Okay, class, welcome back. Today we're going to go over a lot of stuff under the overarching topic of solutions. Today's objective can be broken down into three parts. The first is that we would be able to identify the different components of a solution and the intermolecular forces that are causing them. The second is that we would be able to use molarity to calculate dilutions and stoichiometric problems. And finally, that we would be able to identify strong and weak electrolytes along with non-electrolytic substances. In saying that, let's start up this lecture. If we remember back to last year, a solution is a homogeneous mixture of two or more substances or components. The majority of the components is typically called the solvent, while the minority is usually called the solute. In a solution, this solute dissolves in the solvent. So, in salt water, sodium chloride or salt would be the solute, and water would be the solvent. Solutions can be composed of the following: a solid and a liquid. An example of this would be salt water. A gas and a liquid. An example of this would be a carbonated drink like Coke or Pepsi. And two different types of liquids, or any combination of these three states of matter. The key premise is one dissolves or dissociates into the other. An aqueous solution is a solution that has water as the solvent and either a solid, liquid, or gas as the solute. Sugar in water is an example of where a solid is dissolved into a liquid water, so this would be an aqueous solution. We can also see in the growing trend of having carbonated water, a gas is dissociated within a liquid, so this again would be an aqueous solution. With all this talk about stuff dissolving and other stuff, we probably need to refresh you on the term solubility. The solubility of a substance is the amount of substance that will dissolve in a given amount of solvent. An example of this is 36 grams of sodium chloride is soluble within 100 grams of water, or 36 grams of sodium chloride can be dissolved in 100 grams of water at a given temperature of 25 degrees Celsius. On the other end of the spectrum, if something cannot dissolve in another substance, it is considered insoluble. So, for example's sake, the amount of grease that is soluble in water at 25 degrees Celsius is 0 grams because grease is insoluble in water. We know that when molecules occupy a common area, they have intermolecular forces in which exert on each other. Whether we have a solid dissolving in a liquid, a gas dissociating into a liquid, or even two of the same states of matter forming a solution together, intermolecular forces are present within these solutions. There are three new types of intermolecular forces or intermolecular force interactions between molecules of a solution. The first is a solvent-solute interaction. These interactions are interactions between the solvent particles and the solute particles. The second is solvent-solvent interactions. As you guessed, these are interactions between the two solvent particles. And our final type of intermolecular force interaction would be our solute-solute interactions. As you probably already guessed, these are interactions between two solute particles, or a solute particle and another solute. If our solvent-solute interactions are stronger than our solvent-solvent interactions and our solute-solute interactions, a solution will be formed between the substance. If the solvent-solute interactions are equal to the solvent-solvent and solute-solute interactions, a solution is likely to form. The only time a solution is unlikely to form is when these solvent-solute interactions are weaker than the solvent-solvent and solute-solute interactions. Despite this, a solution may be formed depending on the relative dispersity or magnitude of differences between the forces. Despite these new types of interactions, it is still worth noting that we still have the intermolecular forces taking effect here, like dispersion forces, dipole-dipole, hydrogen bonding, and ion-dipole forces. Those forces are also occurring both in the solute and solvent simultaneously. Now let's start describing a solution's property with the term dilute and concentrate. When we describe a solution, we are going to describe in the amount of solute within the solution. So, a dilute solution is one with small quantities of solute related to the solvent, while the concentrated solution is one containing large quantities of solute relative to the solvent. We can numerically represent a solution's concentration with molarity and molality. Molarity is represented with a capital M and is the amount of solute in moles divided by the volume of the solution expressed in liters. We need to keep in mind that molarity is moles per liters of solution, not solvent. This means we must account for the volume of both the solute and solvent. Typically, when we want to make a solution of a specific molarity, we put the amount of solute we calculate in a flask and then add water or another solvent to a desired volume of the solution. So if we want to make a 1 molar solution of salt water, I would first do my calculations to determine the total volume of the solution. So if I rearrange a molarity equation, we would get that the volume of the solution equals the amount of solute in moles dissolved by molarity. To make calculations easy, let's just say we have 1 mole of sodium chloride. If I now divide 1 mole of sodium chloride by 1 molar, then I would get that we need to have 1 liter in volume. So I would weigh out our 1 mole of sodium chloride, or 58.44 grams of sodium chloride, put it into a volumetric flask. I would then add water until the solid dissolves. Then I would add additional water until I have reached the 1 liter mark, and then mix my solution. Now I would have a 1 molar solution of salt water. One big drawback to molarity is that it's dependent on the volume of a solution. As we've seen in prior videos, volume is dependent on other factors such as temperature and pressure. We can use molality if we want to find a concentration unit that is independent of temperature. Molality is represented by a lowercase m and is the amount of solute in moles divided by the mass of the solvent in kilograms. Notice, molality is defined in respect of kilograms of solvent, not kilograms of solution. Molality is particularly useful when we must calculate or compare concentrations over a range of different temperatures. Now that we know about molarity and how to calculate it, let's take it a step farther. We can use the molarity of a solution as a conversion factor between moles of solute and liters of solution. Let's see how this works in a practice problem. How many liters of 1.25 molar sodium hydroxide solution contains 0.255 moles of sodium hydroxide? My first step would be to identify my givens in this solution, which is 0.125 molar sodium hydroxide, which means there is 0.125 moles of sodium hydroxide per liter of solution. And we have 0.225 moles of sodium hydroxide. Now our goal is going to be to convert our given moles of sodium hydroxide into liters of solution. So I would put my moles of sodium hydroxide over 1, so 0.255 moles of sodium hydroxide over 1. Then I would multiply it by my molarity relationship, or that would cancel out my moles. This means I'm going to have to reverse my relationship for molarity to read 1 liter of solution over 0.125 moles of sodium hydroxide. Now, my moles can cancel out, and we can simply multiply and divide to get an answer of 2.04 liters. In order to save a specific amount of storeroom, laboratories often store solutions in concentrated forms called stock solutions. For example, hydrochloric acid is frequently stored at a 12 molar solution. Fortunately for us, most laboratory procedures do not want a solution that is that concentrated. Otherwise, labs would be considerably more dangerous. In order to make a diluted concentration from a stock solution, we are going to have to use this dilution equation. M1 times V1 equals M2 times V2. M1 is our initial molarity, and V1 is our initial volume of the concentrated solution, while M2 is our final molarity, and V2 is our final volume of our diluted solution. This equation works best because if we would cancel out the units, the unit liter would cancel out on both sides, leaving us just with moles of initial equal moles of final. In other words, the concentration of moles in a new solution does not change. So, how does this look when given a problem? Here's an example of a practice problem. Suppose a laboratory procedures calls for a 3.0 liter solution of 0.5 molar calcium chloride. How should we prepare a solution from a 10.0 molar stock solution of calcium chloride. Since this is a dilution problem, my first step is to write out my dilution equation. So M1 times V1 equals M2 times V2. We know we want our final solution to have a molarity of 0.5 molar and occupy 3 liters, but we are given a 10 molar solution to dilute. This would tell us that we are trying to find a volume of our 10 molar stock solution we need to add to our new solution. So we need to rearrange the equation so that the initial volume is isolated. Or this gives us V1 equals M2 times V2 over M1. Now we just plug in our numbers for each value, so we get 0.5 molar times 3 liters over 10.0 molar. Once we multiply and divide out, we get that we are going to need 0.15 liters of stock solution. Just for your information, the rest of the solution is made up of water and mixed together. Let's continue talking about how math is used in solutions with solution stoichiometry. Now we know that molarity can be used as a relationship to convert between volume of a liquid and the number of moles that that liquid occupies. We can take this and add it to our building illustration for our stoichiometry problems. With the solutions, we simply take the top floor of the stoichiometry building, which is our mass floor, and change it to volumes. Now if we're going to go from volume in liters to moles, all I have to do is multiply my liters of solution by the molarity of the solution, or moles over liter. If I'm going from the moles floor and we want to find the volume that many moles occupies in a solution, all we have to do is invert our molarity, or just give us liters over moles. So if I have a 5 molar solution, that means that there are 5 moles of solute per 1 liter of solution. If I invert that, then that means there's 1 liter of solution per 5 moles of solute. Now, let's work a practice problem. What is the volume in liters of 0.15 molar potassium chloride solution that will completely react with 1.5 liters of 0.175 molar lead-2 nitrate solution according to the following balanced equation? 2 KCl plus PbNO3 yields PbCl2 plus KNO3. So let's write down what is given first. We have 0.15 liters of lead-2 nitrate solution. The lead-2 nitrate solution has a concentration of 0.175 molar, and our potassium chloride solution has a concentration of 0.15 molar. We are trying to find our volume of potassium chloride, so I would put liters of potassium chloride and maybe put a question mark by it so I have that to reference to. Now I'm going to start solving this problem. My first step is going to be in using my building illustrations to go from the volume floor of my lead-2 nitrate to my moles of lead-2 nitrate. I do this by multiplying it by the molarity of my lead-2 nitrate. So 0.150 liters of lead-2 nitrate solution times 0.175 moles of lead-2 nitrate over 1 liter of lead-2 nitrate. This gives me 0.2625 moles of lead-2 nitrate. Now I'm going to use the mole ratio given to me in the balanced chemical equation. This equation tells us that there are 2 moles of potassium chloride to every 1 mole of lead-2 nitrate. Since we're going to try to cancel out moles of lead-2 nitrate, we are going to use a relationship of 2 moles of potassium chloride over 1 mole of lead-2 nitrate. This gives me 0.0525 moles of potassium chloride. Now my last step is to convert my moles of potassium chloride to liters of potassium chloride using potassium chloride's molarity. Because we are going from moles to liters, we are going to have to use the inverted molarity. So our last step should read 0.0525 moles of potassium chloride times 1 liter of potassium chloride over 0.150 moles of potassium chloride. This gives me 0.35 liters of potassium chloride in my solution. Okay, as much as you would like for me to be done with this lecture, there is still one more topic we need to cover with solutions, and that is the topic of electrolytic solutions. If we hook a light bulb and battery up together in one terminal and then hook the other terminals to conductor rods, then we can then place those conductor rods into a saltwater solution and a sugar water solution. And we notice something strange. When the conductor rods are put into the salt solution, the light bulb lights up, while when the conductor bars are in the sugar solution, the light bulb never lights up. Why is this? Well, it has to do with the fact that salt or sodium chloride is a good conductor of electricity while sugar is not. Why is that though? Well, when salt dissolves into water, it dissociates into a sodium plus ion and a chlorine minus ion. When dissolved, these ions can act as charge carriers because they have a positive and negative terminal, allowing a solution to conduct electricity through it. If a substance can dissolve in water to form a solution that conducts electricity, we call these electrolytes. Substances such as sodium chloride that completely dissociate into ions when dissolved in water are considered strong electrolytes. Like our sugar solution, most molecular compounds, with the exception of acids, do not conduct electricity well. They do not dissociate into different charged ions, so there is no terminals for electricity to travel through. Because these substances do not dissolve into ions or conduct electricity, they are considered non-electrolytic or non-electrolytes. Despite acids having some molecular compounds, acids can dissolve into ions too. This is because most acids contain hydrogen cations, and the rest of the acid acts as an anion. So hydrochloric acid is HCl, and yes, it is a molecular compound. But when these atoms break apart from each other, they have oppositely charged oxidation states, making them a cation and an anion. Because all the components of this acid dissociate, this solution is considered a strong acid and a strong electrolyte. Unlike hydrochloric acid, though, most acids are weak acids and weak electrolytes because they do not completely dissociate in water. So acetic acid, HC2H3O2, is considered a weak acid and weak electrolyte because it breaks apart into water to form an H plus ion component and a C2H3O2 minus component. Unlike your hydrochloric acid, which breaks completely apart into a hydrogen plus and a Cl minus ions, the ions we see in our acetic acid has a compound present in the form of an anion, the C2H3O2 portion. This makes this a weak electrolyte, thus it weakly conducts electricity. Okay, so now I think that I've covered enough information when it comes to the topic of solutions. In this video, we covered a wide range of topics, from what are the components of a solution to how to determine whether a solution will conduct electricity, and all the math that goes along with understanding solutions. And saying all that, I hope you learned something from this video. Keep up the good work, and see you next time.